Hello everyone, this is Reshmi Begum. I am a student of Computer Science and Engineering currently in third semester, and the topic that we will be discussing today is work energy principle and its application in plane motion of connected bodies, kinetics of rigid body rotation. So in order to know what we will be learning in this topic, we should also first get introduced to what are the basic terms like what is work, what is energy, and what is this principle all about. And since, as you could see, that our topic also have the word kinetics in it, right? So we should also know what is kinetics exactly. To simply begin with, kinetics is a branch of mechanics that deals with the study of forces and how it affects on the motion of particles in rigid bodies, or in simple words we can say that kinetics is basically the study of motion of rigid bodies while taking force into consideration, and work energy principle is a fundamental tool that helps us analyze the behavior of particles and rigid bodies by considering the work done on them and the changes in their mechanical energy. To know more about work energy principle, we should first get introduced or get along with the terms like what is work or what is energy. So basically work is the amount of energy that is transferred to or from an object by any force acting on it, and energy is the capacity to do that work. And the relationship between the two is that the net work done on an object is equal to the change in its kinetic energy. Therefore, as you can see, the mathematical formula for it goes like W, that is work, is equal to change in kinetic energy. That is Ke final minus Ka initial, and the formula for kinetic energy is half mv square, where m stands for mass and v stands for velocity. And the key concept here is that work is the transfer of energy to or from an object due to work applied over a distance. Work are also of several types. As you can see here, there are positive work, negative work, and zero work. Positive work basically means when force and displacement of the object is done in the same direction. Uh, for example, pushing a box across a floor. And negative work basically means when we are applying force to an object, but the displacement of that object is in opposite direction. For example, friction. Friction always acts opposite to the direction of the displacement. And there is zero work. This is when force and displacement act in perpendicular direction, just like a satellite in orbit around Earth where the gravitational force is perpendicular to its velocity. Now we will learn about application of work energy principle in plane motion of connected bodies. As you can see in this figure, there is a pulley and two masses are connected to it, right? So connected bodies, that is system of bodies that are linked together. It can be linked together with a pulley, a rope, gears, etc. And in this example, we are considering two masses connected by a rope over a pulley, and from what we can see or observe is that if one mass uh, is applied force upon, then it will do the work, right? And that energy will be transferred on both the bodies. That basically means that if m1 moves, that will eventually end up moving m2 as well. And in Therefore, the equation of motion is summation of F, that is force, equal to mass into acceleration. And while taking these considerations, we are considering that work done by external forces is transformed into kinetic energy, and the energy of one body affects the other in the system. Just like we explained earlier, M1 will affect M2, that is mass 1. Any energy on mass 1 will affect M2, that is mass 2. And plane motion of connected bodies, like we explained earlier, two blocks M1 and M2 connected by a light string over a frictionless pulley. We are assuming that the pulley is frictionless here, and if we pull M1, it pulls M2 as well. So the assumptions are that we are ignoring the friction, and we are also assuming that the string is inextensible. Only then, or only under such scenarios, M1 and M2 will react accordingly. And according to our work energy principle, the work done external will be equal to the change of kinetic energy in the total system. And the steps to calculate this is that we calculate the total work done on the system first while considering individual kinetic energies on each block of mass. Moving on, in this slide, we are learning about kinetics of rigid body rotation. And rigid body rotation refers to the motion of a body where all the points in the body rotate about a fixed axis. That is, all the points within the body rotate about the fixed axis without changing the distance between them. And the key quantities when we are talking about kinetics of rigid bodies are angular displacement, that is the angle through which a point or line has been rotated in a fixed specified sense about a specified axis. The second one is angular velocity, which is the rate of angular displacement. As you can see, here is the formula for angular velocity, that's omega equal to del theta by del t, and angular acceleration, that is alpha, the rate of change of angular velocity. And here is the formula for angular acceleration, that is alpha is equal to del omega d omega by d theta. Moving on to our next slide, work and energy in rotational motion. So when we are talking about kinetic energy, as we can remember from what we learned earlier, kinetic energy is equal to half mv square. But when taking into consideration that we are talking about rotational kinetic energy, the formula changes to half I omega square, where I is the moment of inertia, which we will discuss in our next slide, and omega is angular velocity, like we talked earlier. And work done in rotation, in case of rotation, is calculated by W is equal to torque and change in the angular displacement, that is del theta. Now, what is moment of inertia? Moment of inertia represents an object's resistance to changes in its rotational motion. It depends on the mass distribution relative to the axis of rotation, and it is represented by the equation I is equal to summation of mi, that is mass of the particle, and ri square, that is the distance from the axis of rotation. And if we are to give an example where moment of inertia can be taken into consideration, is that moment of inertia of a solid disk rotating about its center. In such a case, the m will be mass of the disk and r will be radius of the disk. Moving ahead, we are also to discuss the application of work energy principle in rotational motion. And for such a case, we can take an example of a disk rolling without slipping. In such case, a disk has both translational kinetic energy, that is moving from a point A to B, that is moving along the surface, and rotational kinetic energy, that is spinning about the center of the disk. And the total kinetic energy of the disk will be the sum of these two, that is the rotational kinetic energy plus the translational kinetic energy. And this is how we calculate translational kinetic energy, that is how we calculate actually normal kinetic energy, that is half mv square. And when we are taking the rotation into consideration, that is for rotational kinetic energy, we will be calculating it with half I omega square. And in this case, we apply the work energy principle. We can calculate how much work is needed in order to set the disk in motion, or how its energy changes during the motion. And how work energy principle is applied in engineering and mechanics is that we can see in cases of gears and pulleys, or in cases of rotating machinery, understanding rotational energy and torque helps optimize their performances. And that is how in real life, or in engineering and mechanics, work energy principle is used. In the current slide and the following slide, there are two sums related to work energy principle that are already solved step by step, along with the explanation for each step. And if needed, we can pause this presentation video and go through the question or the solving method of how we solve these questions related to work energy principle. This is question number 2 for the same. Lastly, I would like to summarize that work energy principle is fundamental to understanding energy transfer in both linear, that is translational, and rotational motion. It enables us to analyze energy exchanges in complex systems, particularly when dealing with interconnected bodies, such as we discussed, like bodies that are connected through pulleys or gears, etc., moving in a plane. So connected bodies in plane motion. This principle helps in analyzing the energy exchange and movement of interconnected bodies, such as those connected by string or rod, like we discussed earlier, or kinetics of rigid body rotation. This branch of mechanics involves concepts like angular velocity, angular acceleration, and moment of inertia, and work energy principle plays a significant role in understanding the energy dynamics of rotating objects. And real world application of the principle is that it is the principle discussed are applicable in mechanical systems such as pulleys, gears, rotating machineries, and numerous other engineering applications. With this, I would like to conclude my presentation. Thank you.